Good afternoon. Welcome to MATLAB Chapter 3. Today I am talking to you from my spare bedroom, and we'll be talking about how to write programs in MATLAB. All right, so to get started, let me go ahead and just share my screen with you. Let's see, we have PowerPoint for you, which you can download and follow along with on Moodle. And this is backwards. Let's hold on 1 sec. Let's escape settings. Okay, let's see. Can you see the slides? Probably not. Oh, yes. Now you should be able to see the slides. Okay, so great. This is going to be our introduction to MATLAB. Let me just make sure you can see the slides. Hold on. Let's do this. All right. Display settings. Okay, let's see. I think that's good. Hopefully you're able to see this now. Okay. Except that you cannot see mine. Oh, yes. Okay, we're good. All right, so bird's eye view, what we're going to talk about today is algorithms. What is an algorithm, and why should we know what they are, and how do we make one? We're going to talk about making MATLAB scripts. We're going to have input and output. Then we'll talk about writing scripts that have input and output, starting with really simple ones that just have one parameter, and then we'll talk about ones that have multiple parameters. We're going to talk about scripts to write plots, file input and output, what are the load and save commands for. Then we'll talk about user-defined functions, how to make them, and we'll actually practice with a couple of them. And then also we're going to talk about local functions in scripts, how can you call them. And finally, we'll talk about commands and functions. How are they the same and how are they different? So today is an action-packed lecture. So let us get started. So algorithms, why should you learn how to program? Well, and this is related to algorithms because algorithms is how we convey that information to the computer. So the reasons why we might be interested in programming is to interact with the computer on your own terms, to automate repetitive and or laborious tasks, wants to do that, to bring your ideas to life. You can use computers to do certain tasks much faster than humans can do. I use this for simulations all the time because if I had to calculate F equals ma a million times by hand, I would be much slower than my computer. And why did you decide you wanted to learn how to program? There are many reasons why we might want to do this. So this brings us to the topic of imperative programming languages. Imperative programming is a paradigm that explicitly tells the computer what to do and how to do it. This is typically what one thinks of when they think of writing a programming language. However, there are in fact other kinds of programming languages besides imperative programming, which are more about we tell the computer what we want to happen and the computer figures out what to do. Some examples of programming that falls not in the category of imperative programming is artificial intelligence and database programming. However, these topics are outside the scope of our course. We're going to be talking about imperative programming in this course, which requires an algorithm to go from your idea to the computer actually computing something. That means that we're going to need a programming language to communicate that algorithm to the computer. One thing that's sometimes confusing to people is what an algorithm actually is. The algorithm is not necessarily code itself, although a code can embody an algorithm. Algorithms are the steps in order to make something happen. So some examples of imperative programming languages include Python, C, C++, C#, Fortran Basic, and MATLAB. And as mentioned, there are some other kinds of programming languages out there. So declarative is an example of a kind of programming that is not imperative, such as when you want to do machine learning, which is, again, beyond what we're going to be able to handle in this particular class. It would be an advanced topic. So this is an example of an algorithm. This is Euclid's algorithm for the greatest common divisor of two numbers. What that will do is it will compute what the GCD is going to be between any two numbers. So you might look at this and say, that doesn't really look familiar. That's not how I figured that out when I was in school. So what's the greatest common denominator between 9 and 6? As I'm sure you know, that's going to be 3. So what we do in an algorithm, however, is we provide the computer with step-by-step instructions as to what to do in order to figure out what the answer is. So I would definitely encourage you to take the time to actually step through this algorithm to see if you can compute the GCD and if you couldn't get 3 as the answer. You might surprise yourself in that you do arrive at the correct answer, but it's not necessarily in the way we might initially think of to do it. Another thing that's interesting about this algorithm is that it's not specifically in any programming language. This points out the idea that in imperative programming, an algorithm is not necessarily tied to a particular kind of code. It could be written in Python, and as a matter of fact, if you take my Python class, you will code this up in Python, and we could just as easily code this up in MATLAB as soon as we learn a little bit more skills in terms of actually writing code from scratch. So let us just think about what it means to parse syntax. So this is a quote taken from Harper Lee. And so Harper Lee is an author that wrote To Kill a Mockingbird, which is a famous book that's read in many high schools, and you might have read this book. And so this has a really nice quote in here that I like. Real courage is when you know you licked before you begin, but you begin anyways and see it through no matter what. So that has some particular meaning to it on a number of different levels. And if you were to be taking an English literature class, you might spend a whole class talking about symbolism and extracting meaning from text, such as this. When we're talking about programming, we're also talking about a similar thing. We're talking about how do we get the meaning out of what is given. So from mathematics, we might get the meaning out by doing order of operations, remembering the parentheses, exponents, multiplication and division left to right, and addition and subtraction from left to right, is how we can parse out what the meaning of an expression is. That is, to get out what the actual number that it's equal to. And so this is showing you how that could happen. In literature, we would parse something by figuring out what the meaning means to you, perhaps by invoking symbolism, or maybe looking at things such as the setting and the time that took place and so forth. So in computer programming, we need to think about how is the computer going to get out the meaning of what it is that we're telling it to do. So we have this idea in an algorithmic form, and we want to somehow bring that over into some meaning that the computer is supposed to do what we want it to do, when all it can do is work with zeros and ones. And so that's what parsing is all about, and this is why we need to have algorithms and a programming language to mediate between that algorithm and what it is that we actually write. And that is where writing scripts and learning how to program come into play. We'll begin talking about how to write algorithms into code for a major part of the rest of the class. What we'll talk about today is how to make a MATLAB script. In the subsequent lessons, we'll talk about how to do things such as flow control, that is, if, or while, or writing loops of various types and kinds. So we'll learn how to deal with those things in upcoming lessons. But for today, what we're going to learn how to do is how to write very simple programs that run from top to bottom, that is, having linear architecture. So in order to get started with this, we need to learn how to write a script. And a script is basically just putting some commands into a file. And in MATLAB, these script files are going to be called M files. So to go from an algorithm to a script, we need to actually write the program. So an algorithm is developed to solve a problem, and it needs to be written into a program in a particular programming language, such as MATLAB. A computer program is going to be a sequence of instructions in a given language which accomplishes such a task. To execute or run a program is to have the computer follow the instructions sequentially. So this just gives an overview of how this process works. So we typically program in a high-level language, and then it's going to go into machine language, that is into the zeros and ones the computer is going to use in order to actually figure out what to do. So our job is to write this program up here. There is such a thing called a compiler, which is going to mediate between the program, and this is representing a computer chip on your computer. So programs such as MATLAB are called high-level languages having English-like commands and functions, although they still have complicated syntax and have to be written in very exact ways. But certainly we can understand it much better than a series of zeros and ones. Computers, however, only interpret machine language, which is in the zeros and ones, so it's therefore necessary to translate between the code written by humans and the code interpreted by the computer. The compiler is a special kind of computer program that takes the high-level source code and translates it to a computer executable code, which let's call that runnable code, which is called the object code. That is one way of talking to your computer, is to use the compiler. However, there's also another version, and that's called the interpreter version. So this is another example of a high-level language that is English-like in nature. However, the strategy is a little bit different. An interpreter also converts the code for execution by the computer instead of processing the whole file at once, which is what happens in the previous example. The interpreter version is going to move through the code line by line, translating and executing each command as it goes. Thus, we say that these programs are interpreted rather than compiled. So the compiled version is going to process the whole thing at once, and there'll be a chunk of code, and that whole code will go all at once. Whereas in the interpreted version, each line of code will be sent off to the computer processor one line at a time. And so there's a slight difference between interpreting a program and compiling a program. MATLAB is of the flavor that is interpreted rather than compiled. So therefore, now we need to make a script. So this is just going to show you quickly how to actually go ahead and make a script. So there's a couple of ways you can access this in MATLAB that are both pretty simple and pretty intuitive. So you go home, new, and script, which you can do right in this section over here, or you can use, from the home menu, you can use this plus button to make a new script. You just where it says new. And then what will happen is your MATLAB will pop up, and here you have a window, and this is your area to type your script. Notice that your command window still exists, it's just down underneath here. So the idea is you will write your script up in this window up here, and then you will write your commands as you've been doing in the previous 2 weeks down here and continue to use those. You can use your commands also to run your scripts. Let's talk about documentation. So in most every programming language, there's the possibility to put comments into your program. That means you can write something that doesn't actually become part of the code. The purpose of the documentation is not for the computer, since it doesn't interpret it anyways, but it is for the humans who will read the code. It's for your future self, and it's for others who might use your program so that they know what the program does. The way that we indicate comments is we use the % symbol. If your comment appears beginning at the line, then the percent symbol goes all the way to the left, and everything to the right of that will be a comment, which we see here because it turns green. You can also use this to put a comment at the end of a line, so your line could contain some code, and then you could explain that with a comment at the end of the line. The percent sign is going to begin all the comments. You should always comment all your scripts. Comments are not executed, as we mentioned, because they're for humans. They're ignored by the compiler or the interpreter. You can use a comment to put a heading on all your scripts for this class. You should use the style shown over here. Up to this point, I've allowed you to turn in file formats at whatever your choice. However, moving forward, we should be moving into turning in MATLAB script files for your assignments, that is for your homeworks and for your labs. You should put your name, our course number, which is QAC 154, and the date, and then a brief description of what the script does. Whenever you want to explain how your code works is when you should use a comment. So let's talk about input and output. Starting with input, what we want to do is we want to obtain information from the user. So how can we do this? The syntax is a variable is equal to input, and then we need to put a prompt. So let me just take a moment to describe to you how we should read this, this information that I'm giving to you. These angle brackets here are telling you that you need to type in some information. So that means you need to put in your variable name inside here. We do not actually type the angle brackets. They're just indicating for you to fill it in. Things that are not explicitly in the angle brackets means you need to type it. So this input is going to be a keyword in MATLAB that you explicitly need to type. The same is true of the parentheses and the quotes. So what you need to do is you need to type your information. You need to type your prompt in here, and then that will prompt the user to type some input. Okay, so for example, suppose we want to obtain a radius. So we could say radius equals input, enter the radius. The point of the text is so that when this is running, that the user will know what they're supposed to do when it stops executing, being paused, waiting for them to type something. So if there's no information there, then the user won't know what to do. But if you put this here with a prompt, then they'll know why the cursor is paused and they'll know what to do. So in this case, the user typed 5, and then this reports back radius is equal to 5. Capturing the input in the string format. It's important to realize that when we use the input function, that the type of the variable that is obtained is going to be formatable. If the input type will be a string, that is characters, then you must specify a formatting element. You can use the formatting element S to indicate that you want a string. The user may also indicate the type by using single quotes around their answer. So this is some examples of what that would look like. So we have syntax variable equals input, and then here's the message for the prompt, and then right here you see that we're putting in this formatting information. So this single quote around the S is indicating that the type of what the user types will be a string. It will be converted into a string if the user types something else. So for example, letter equals input, please enter a character, format S. So here we run that and it says, please enter a character, and the user typed A. And then you see we do letter equals A. So when it reports back what the value of it is, it automatically comes back with the single quotes on it, which is going to indicate string. Recall that single quotes are for strings. Now, let's consider another way that this could be done. So we could have a variable, called name and say, please input your name. Now notice that S is not specified. And now when I press return and it prompts me to enter my name, I'm putting my name and I am specifying my name is of type string because I'm typing those single quotes. Note that the single quotes here are not included in the variable itself. It's just to indicate the variable type. So here that's being shown and we have the quotes. Vector input. So suppose you want to get a vector is the format for the input. That's possible to do. Valid vectors can also be used as input. The type is automatically detected and there is no specific formatting element required. Remember that in MATLAB that the default is going to be working with vectors and matrices. So it's very natural that that would be the default format here. So here we have b equals input, please enter a vector. And here we press enter and it prompts us, please enter a vector. And notice that the user has used the augmented assignment way of creating a vector with elements from 1 to 5 inclusive with a delta of the default value of 1. Now, suppose you want to get some output. So we have the output statement disp for display. The disp command displays information to the screen. It's used to display the result of an expression or a string or character array without assigning any value to the default variable answer. Right? Because if you do not specifically set up a variable, then it will be sent to the answer variable by default. This particular way of doing things does not allow formatting. So for example, here's our syntax display, and then you have your text or expression in there without any formatting. So here's an example over here. If I set up a variable called name with my name in it, Kelly, then I do display name, and my name then gets displayed on the screen. We also have output statements, fprintf, and this is printing with formatting. So this means that we can then select the way in which the information will be displayed on the screen. So the formatted print command fprintf allows the user to specify an output format, of which we have several to choose from. It takes a format specifier, and these are the format specifiers over here, which should be somewhat familiar at this point because they very closely match to the types that we've already discussed. So the format specifier can be either a character vector, which is single quotes, or a string, which is the double quotes, but the prompt in the input statement must be a character vector. New line character /n is used to specify a new line. So what this /n means is this is the escape, which says that it's going to be a formatting command, and then n stands for new line. So whenever you have /n inside of something, it will cause a new line to be printed. Let's take a moment to look at the different formats that we have available. So %d is going to be integer, it stands for the decimal. %f is going to stand for float, which is going to be a real number. %c is a character, which indicates one particular character, and %s is for a string of characters. So here's an example of what fprintf would look like, the value of %d for sure, /n. And then we have an expression down here. So notice that what happens is this %d becomes like a variable. It becomes a placeholder for something that's going to get filled in. And the thing which is going to get filled in is the expression that follows. So 4 to the 3rd power is 64. And by putting this expression just like this, this will format the 4 to the 3rd power into the decimal format. We can also print vectors and matrices. When working interactively with printing a vector, use the /n for the new line to specify a return after each entry in the vector. When this is done, each number will be on its own line, whether or not it was a column vector. The new line can be omitted, but it will print the next prompt on the same line, which is a little bit inconvenient. In a script, this problem is easily avoided by using a separate print statement with the new line character. So let's just take a look. This here is an example of a vector having 2, 3, 4, 5 as the values in it. And when we do printf with fprintf with this %d and the new line after it for the vector, you see that a return gets introduced into it. So it appears as though it's a column vector, even though actually it's not, it's a row vector. So just be aware of that anomaly. Here we're going to demonstrate printing of a vector. So here's a vector 2 to 5, and if we do fprintf %d of a vector and then we print it, then this is what it would look like from a script. Scripts can take input and output. So suppose we wanted to set up a script that's going to calculate the area of a circle. This script is going to calculate the area of a circle. It prompts the user for the radius. Note that they have a very nice formatted heading on this script that explains what this script is going to be about. Then we're going to have some information about which each section does. Prompt the user for the radius and calculate the area. And second, it will print all the variables in a sentence format. So those are the two main areas of this first script. So we're going to have a formatted print. Note the units will be in inches, right? Okay, and then we have a new line here, so there'll be a return, and then we have this expression here, radius equals the input of, please input the radius. So this, when it executes, will prompt the user to input a radius. And then that value will be stored into the radius variable. Now, having a value for the radius, we're able to compute the area. Area is equal to pi times the radius squared. Radius value came from the previous line where the user supplied the input. Pi is a built-in Python constant, and so it does not need to specifically be defined. Suppose we want to write out the answer. What we're going to do is we're going to print this out to the screen. Notice that we have a very nice format here where it's in a sentence and all of the information is plugged into the sentence. Another thing that's exemplified by this example right here is how to wrap a line if it's too long. Suppose you can't fit it all in one. What you can do is you can use this ellipsis here, the 3 dots, which will allow you to wrap it around to the next line. Here is an example where it states for a circle with a radius of point. So this is floating point with 2 decimal places after, and then it will report it in inches. Now, this is the place where a variable will be substituted in because this is the formatting part, and radius is the thing which will be substituted into there, which is the variable that's given after this line. The fact that the line split here and the radius is on the next line is not significant. What is just significant that this is going to be the new radius. The line break could have occurred at any number of places in here. Finally, we have print the rest of the sentence. The area is, and then it's going to format that area in inch, and it will tell in inches squared. So the value that will be substituted into this statement right here is going to be the area which is calculated above. Now that we've written the script, it should look something like what's being shown right here. This is a picture of MATLAB being run on my desktop. So what you can see is up in this scripting area up at the top that I've filled this out. I have a heading on my program. I've identified my name, the date, the class that I'm taking, and what I'm working on, which is my Chapter 3 test script. And there's a description here of what's going on. The script calculates the area of a circle and it prompts the user for the radius. And then we have the code that we've just been working on in the last slide. So then if we want to go ahead and run it, what we need to do is first save the script. Click on the save right here, and what will happen is that we'll save it in the current working directory, and you'll be able to see it over here in this current folder pane if you follow this format, which I recommend that you do. What I'm saying is you shouldn't just save your scripts in any file wherever you feel like it. You really should be using the recommended file so that it will work better when you're using MATLAB. Then the next thing we're going to do is we're going to press the run button. That's this green play looking button right up here. The output then is going to appear down here in your command window. So your command window doubles as 2 different things. It doubles as one, first of all, where you can type your programs to test them out, as we've been doing for the last couple of weeks. Second of all, it serves as where your output will be shown when you actually execute a script. So here's the script, and this is where the execution of it is being shown. Notice that this script is interactive, requiring the user to input a radius. This is showing you how that would happen. So it says, please input the radius, and the cursor will in fact stop here. So the user needs to actually type the number and press enter in order for the script to continue, which is happening down here. The output will appear in the command window, and it will fill in the radius. The user needs to fill in the radius when prompted. And then you see that this nice sentence that we have set up down here with 2 values to substitute in happens down here, and that it's been substituted in. The other thing to notice is that we have this formatting command here and another one right here. And what these are saying is that you should substitute in that it will be used out to 2 decimal places, because that's what the percent 0.2, right? So that means after the decimal point, there'll be two fields in there. So the ones in the 10th place will be displayed, which is what we see over here. Now, suppose we would like to do some graphing. Let us consider creating some scripts that are going to do graphing. So our very first graph is going to do the exciting task of plotting a single point. This is the graph being shown right here that MATLAB will generate for you. So this is a simple script that plots one point. What this does is it creates the coordinate variables and it makes a plot in red with a star. So here we have set some values, x equals 11 and y equals 49. This gives the tuple pair for the coordinates of x and y, which is the familiar format that you've used in graphing from your high school math. Then by giving the command plot xy, it causes the plot to be created. This R here in the quotes with the star is a formatting that's going to dictate what your graph is going to look like. So R is for the color red and star is for the type of a point that will be made here. So we see that in fact we have a red star appearing on this graph. We're also applying some labels here. On the x-axis we have time and on the y-axis we have temperature. We also are going to put a title on this, and this title says temperature versus time. Note that that is going to change what is displayed right here at the title. Why stop there when you can make even more exciting graphs? So we could also plot with vectors. This is the simple script that's going to plot one point, and now we're going to edit that to make it more exciting. We're going to edit it to plot a whole vector. So we're going to create a variable and plot with red stars. So here we go. X is going to be equal to 1 to 5. So here we have that this is running from 1 to 5, and Y is going to be these values here, 2, 4, 16, 32, and 64. It looks like an exponential growth. So then when we do plot X comma Y, then this is going to create the plot. And then what this R and star is going to do is this is going to format what the line will look like. Again, R is choosing the color red for this series on the graph, and the star is determining what kind of marker will be used. The star is for these star symbols that appear here. Here we're also going to have the label axes again. So X and Y axis label is time versus, temperature versus time. And we're going to put the title on temperature versus time, which again points up to what goes in the title bar. Not only can we plot numbers that way, but we can also plot functions. MATLAB again has a number of built-in functions which can be quite useful. So here we have some x is equal to 0 to pi over 100 times 2 pi, right? So basically this is going to take you through 0 to 2 pi down here on your graph. So if you remember from your trigonometric studies, that is one cycle through a sine graph wave. And so what we're doing here is we're going to plot the sine graph and some variety of those. So here what we're going to do is we're modulating the amplitude. Y1 is equal to 3 times the sine of x, which will change the y-axis. So you see that it's multiplied up so that the amplitude is larger. So the standard sine graph, as you might remember, has just 1, right? It has a height of 1. And this one being multiplied by 3 will be 3 times higher. Y2 is 1.5 times the sine of x, which is the orange one, and Y3 is plain sine of x, which is the yellow one. Notice that the max and the min are positive and -1 respectively, and Y4 is going to be diminishing the height of those. So here we're going to plot all of these things here. Notice in the plot command that we have a variety of values being specified. X, Y1, X, Y2. So notice that the X's are always going to be the same. That means that we're always using the same X axis here, which is very useful when you're plotting something on the same set of axes. And then the Y values are what changes. We have Y1 through Y4. They will be taken in as a pair, so an X and a Y pair, and that's basically how it's going to work. Again, we're going to put a title on here, plot of sine functions. So this points out the fact that it's not necessary to put your formatting things in a specific order. They will just appear on here as you like, because we had the X and Y labels before the title before. So again, it's just a scripting language. Here we have labels on the X-axis and on the Y-axis to show what those values are. And we also here are showing that you can put a legend on here. That's what's going to give rise to this little box right up here that has a legend for everything that's in your graph. And then we're going to plot X, Y, and then style color marker is going to do some formatting for you. So there is a variety of plot attributes of which we have talked about a couple. These here are not an exhaustive list, but is very much the ones you would most commonly use. So for example, the symbols for the color are given here. We've seen red, black, and a couple others. These are the color choices that are built in. Next, we have the symbols for the markers. So this is going to show what the line will look like. So a single dash will be solid and a double dash will be dashed. This colon will be dotted. The dash dot will be a dash dot line, and none means that no line will be displayed. We also have the symbols for the markers themselves, which is shown here. Notice that there's no overlap between the symbols that are used in the symbol column for markers, for lines, and for colors. They're all unique so that you can use them in any order when you're specifying which one you want to use. These are going to then figure out what the marker is going to look like. Plus is for a plus sign marker. O is for a circle. This star asterisk, as you've already seen, makes that multi-branch star. Dot gives you a point, X gives you crosses, S is for square, and D is for diamond. Not only does MATLAB do those kinds of graphs, which are basically X, Y scatters, but also has the ability to do a wide variety of additional plots. We don't have the time to discuss every single plot type, nor do we necessarily need to discuss all of them, because MATLAB being set up in a very systematic way will allow you to quickly select whichever plot it is you want. And because they all operate in a really similar way, it will allow you then to use what you know about one plot type to generate whichever kind of plot it is that you want. I would recommend using the plots tab shown here in order to explore what other kinds of plots you might want to use. You just click on plots and we see that a whole ribbon of different kinds of plots is going to appear here. So for example, if you wanted to select another kind, you would just pick on that, and then you would be able to make the graph, because the wizard will help you to do that. There's a number of commonly used 2D plot commands. So for example, plot XY is the one that we've used the most up to this point. That is a 2D line plot. You can select the different plot types using point and click off of the ribbon menu that I just showed you. However, each of those just has a command, and by clicking on those bars, what you're really doing is you're really just executing one of these kinds. So the different types that there are the F plot, which is a plot, expression, or function, the bar graph, bar H, which will be horizontal bar graph, histogram, which is going to count up a number of things, that takes the X and Y and will display as a histogram. Area is going to give the 2D area plot. Filled, the pie will be your typical pie graph, you know, the circle ones. Scatter, XY, will be a scatter plot. Contour will give you a contour plot of a matrix A, and log is a log scale plot. We can also graph three-dimensional objects in MATLAB, and this is fairly simple to do because the graphing of these pretty much follows the same format as graphing in 2 dimensions. So here, for example, we're going to have XYZ equals sphere 20, and then we can do surface of XYZ. This graphing in 3 dimensions is done by essentially laying a surface over a series of points. Therefore, we start by specifying what that object is going to be, and then the surface is fit over the top. So this is going to be 3 21 by 21 matrices, and is going to display a sphere. This is an example of what graphing a sphere will look like. We can also graph a cylinder. So this here is showing you what the MATLAB cylinder looks like. Cylinders allow for more manipulation than spheres because we can change the shape of the walls. We can plot a cylinder with nonlinear walls using the code below. This is basically taking the parameterization way of doing some graphing. If you've done some advanced graphing with your graphing calculator, you would be familiar with parametric equations and drawing those. They're slightly different than functions in that you can have more than one x and y values corresponding with each other. It's more that you just keep track of what the x and y values are as they're traced out in time. The cylinder is a typical exercise you would do on your graphing calculator, and therefore it's a natural one to choose in MATLAB. So t is going to be the parameter, which is usually understood to be time. So it's going to go from 0 to 0.1 to 2 pi, right? So we're going to use increments, these small increments, to go up to 2 pi one cycle. And r is going to be equal to 3 of sine t. Then we're going to have x, y, z is equal to the cylinder of r, which will create the cylinder. And then we put a surface on that. You see it is being built up using this disc-like way of seeing things. And then we're going to shade it for interpretation. And that's what gives us these nice colors to see the gradation of the different slices through the sphere. Through the cylinder. We can also explicitly do graphing using parametric equations. So suppose we have a function of the form, so here we have z equals f of x plus or minus g of y. And so x and y are independently varying variables. And so in this case, we'll be graphing z equals x cubed minus y squared. First, what you have to do is define x and y. So x is going to be on negative 100 to positive 100 with a delta of 1, and y is going to be on negative 1 to positive 1. We see over here, right? So this is the y scale. This is the x scale right here because they match to the domain and range that are specified here. So then what we can do is write the following code: x, x, y, y equals mesh grid of x, y. And what this does is it creates a mesh grid using the vectors x and y to create the rectangular grid. Now we're going to have z is equal to the relationship between those two things. So we've said that we're going to do x cubed minus y squared. In order to do this, we're going to have xx, right, dot cubed and minus y squared. And so then what we're going to do is take the difference between those, and then we're going to go and put those results on the figure, and here is the surface of fitting those things together. And then we color it by using the shading command. That will result in the surface being shown over here. So there's a number of basic 3D plots that you can use. And there's not only the surface one and the sphere and so forth that I've just shown you now, but there's also a number of them. What you should do is you can discover those using the ribbon at the top, or you can look up these commands. So here's a series of what's available. The plot 3, which is 3D line plot, bar 3, which is 3D bar graph, bar 3H, which is the horizontal version of it, and a 3D pie chart. 3D scattering, contoured in 3 dimensions, surfaces in 3 dimensions, well, surf, which is shaded surface plot, and then there's the regular surface. Object, then we have mesh, which will give you a mesh plot, and fsurf, which is the 3D surface. Fmesh is plotting in 3D mesh. Cylinder, which we've just taken a look at, is going to create a cylinder for you. We also have ellipsoid, and finally sphere, which we've also had a look at. So then, now that we know how to make a script to do some graphing, let's take a look at file input and output. So modes of files are to read from a file, to write from a file, and to append to a file. These are the 3 things that we can do with files and the major functions that we'd want to have for one. You're probably very familiar with these from already using files in other contexts, such as writing Microsoft Office documents and so forth. How to write a matrix to a data file. So suppose you have a matrix in the memory in your MATLAB and you want to write it to an external file. This is possible to use when we're going to write to an external file. This is going to use the save command to write the data to a file. The file should have the .dat file type. We're going to use ASCII format to write the text or the data file. A file containing the data from a variable is shown below. Note that the file will appear in the current folder. So here's our current folder pane over here, and notice that a new test file.dat appears when we do this down here. Here's my matrix, and this is going to have a random number generated between 2 and 3. No, in a 2x3 format. So here is my matrix, and those are the random numbers that are generated. And now what we can do is we can save that. So we use the save command, and we give the name of the file, testfile.dat, and then we're going to have my matrix in the ASCII format, and we see that voila, a matrix is created. Suppose you want to review the contents that are in a file. So the type command can be used to view the contents of the data file that you've just created. Notice the contents are displayed using the scientific notation, which may not be what you expect. Just to bring back to mind how scientific notation works, what this is showing you is this is showing you 1 digit before the decimal place, and then this is going to tell you how to move the decimal point to get out the number that it actually describes. E means times 10 to the power of, and the negative means moving the decimal point to the left to make it smaller, and a positive value means moving it to the right to make it larger. You see that all these numbers are going to actually represent data that is less than 1. Suppose you want to add more data to the file. This is what appending is. So what we're going to do is we can use the save command with the append qualifier instead of the write qualifier, so that it won't clobber the data that's already there. Forgetting the append qualifier and specifying the same file name as an existing one will cause your data to be overwritten. Bad idea, don't do that. The example shows how to create another random matrix and append new data to the already existing file. So what we're going to do is we're going to use the command save, and we'll give the file name .dat. So they should all be .dat, so I left that outside of this. So that is how you'll recognize that file format. And we have the variable name, and then the ASCII and append is what you use to actually write that data out and doing the append. So here we go. Here is a matrix, and then what we're going to do is we've saved this the first time, and now what we can do is we can type the test file.dat to verify that the new data was in fact added on. So the next thing you'd probably want to do with it is you probably want to actually read the information in. That's using load. So you use the load command to read in data from a previously created file. This is very useful because you might save something and want to go back to it at a later time. This can be read into a matrix variable. The matrix variable will take the same name as the file without the file extension. So if you need to get into a file called testfile.dat, you're going to use just test file. Because of the user who is going to see which variables exist, which can be useful before you issue this command. So here we have load file name .extension, and here's an example of doing that. So you do load testfile.dat, and now we're going to ask what are the existing variables. So we use who to find that out, and we see that the variable is test file, which was automatically determined from testfile.dat. Here it is, and here's our matrix with all of this data in it. So then why stop there? Maybe we would be interested in building up user-defined functions. So a function is gonna, what is a function? A function is something that's gonna allow you to make a call out and to calculate something particular and then send that value back to the point of which it was called. This is what a function is. What functions do is they allow you to do one specific task per function. When you have a function call, you're going to provide it with some parameters, and then those parameters are going to cause some particular value to be calculated by the function, and then that information can be conveyed back to the caller. So for example, perhaps it carries out a calculation for you. The parts of a MATLAB function. In MATLAB, it returns a single result, which is going to consist of the following. First, you're going to have the function header, which is the first line comprised of the word function to indicate that it is a function. Then the next will be the output argument, followed by the assignment operator equals as the function returns a result. So that becomes a variable inside the function that will be returned. This is presumably the one that will contain the answer. The name of the output argument followed by the assignment operator equals is going to be the result that gets returned. The name of the function, which is important because this should be the same as the username of the file in which this function is stored to avoid confusion. The input arguments are going to be in parentheses, which correspond to the arguments that are passed to the function in the function call. A comment that describes what the function does. This is printed when the help is used. So this is why we're going to follow the general standard for doing the naming. The body of the function, which includes all statements and eventually, must put a value in the output argument. Finally, end appears at the bottom, and end is at the end of the function. It's not necessary in many cases in current MATLAB, but it's considered good style to do it explicitly. So here's an example of the general form. What we have here is the name of the function, which is being displayed in the book, but you don't actually type this. Then here we're going to have is the function to cause a function to be made. This is the name of the argument that's going to get returned. So that is what's happening here. And then it's equal to the function name times the input arguments. And so the input arguments then would be sent out to this function over here. So then we would have a comment describing the functions. Then what we're going to do is we're going to have our statements, our statements here. These are going to include putting a value in the output argument as one of the things that it does, because if the output argument never gets a value, then when it gets returned, when the function ends, there will be an error. Then we have this end tag to indicate the end of the function. Here's an example of a function. It's very simple. You see that we have the declaration at the top. Function, we have the name of a variable area equals calculation and radius. And so the RAG then is going to will be the input parameter. This is going to calculate the area of the circle, and this is the format of the call specified here. So you should follow this way of setting things up. This is going to take in the radius, and then it will return the area. Here we have the actual code, area equals pi times radians, and then we see that the function ends. Suppose you want to view the contents of a function. What you can do in order to do that is use the command type. So use the command type to view the contents of a user-defined function. Built-in functions are stored in star.m files, which are also called m files, and they can also be viewed with the same command. So this is the syntax of the command. We have type, which is the command itself, and then you give the name of a function. So here's calc area, an example given in your book. When we type calc area, then the function is displayed on the screen. Suppose you want to actually call the function to use it. So then what we're going to do is we're going to use the function name followed by any parameters required. This is similar to using MATLAB built-in functions. Here's the syntax. Use the function name, make sure you include the parentheses, and then put whatever your input parameter is right in here. So here's an example, calc area 2. So this is a function, calc area, and the parentheses are mandatory per the function format, and then 2 is the value that's being passed in. So the answer will be 12.5664. Why stop there when you can call your function from a script? So maybe you're going to have a script and you want to calculate something that you've already written some code to do. So you can in fact actually do that. Let's take a look at how. The function calls come from inside a script file. So here is a script file, and this is going to have a function call. Okay, so here we're computing the radius, and here we're making a call out to calc area. So notice the calc area.m also exists. It's just in a tab that's behind. It's not necessary for it to be there. I just happen to have been working on it at the same time and hadn't closed it out, so it's still there. So this is what's going to happen. We're going to run the script file, and it's going to cause the execution of the script file to execute, which will call the user-defined function. The user-defined function is calc area. So here we see how this is going to work. Here is the code for the circle call function, and then that's going to call out to the calc area.m file. here is what it looks like. This is down in the command prompt. We use the circle call function call right down here, which is going to execute this script. Looking at the script, we see that this script does not take any input. What it does is it prompts the user for the radius. So radius here is equal to the input of please input the radius. Then the next thing that's going to happen is the area is going to be calculated. So here is the area equals calc area of radius. Notice that this is in fact actually a function call to our calc area function that's user defined that's right up over here. So we're going to do that, and then that will send out that information to the calc area. Then what we're going to do next is we're going to format the printing statement for a circle with the radius of %2f, so that's floating point with 2 decimal points, which is going to report the size of the radius. And then we're going to continue that over here. The area is 0.2% in new line, so that's going to end up going onto a new line, and the area will be substituted into that right there. Let's just take a moment to compare the user-defined function with the script. So there are some things that are the same about them and some things that are different. I've just pulled up function area, which is so the calc area one, which is in fact actually a function, and I've pulled up the circle call function script. Notice that there are some things that are the same. Both of them are stored in M files, and they both can be called from the command line because we've done that with each of them. However, there are a number of aspects which are different. A function must begin with the keyword function. So here you see that it begins with function, and here it does not. A function must end with the keyword end. So notice that it has end over here, whereas this one does not. A function has a specific header format. So we have the name of it, well, the function declaration, and then we have the name of the variable that it's going to return, and an expression that relates how it will be calculated. A script file cannot be called from another function. That's an important thing to note. A script may be called, may call a function. So we saw how this script right here, the circle call function actually makes a call out to the circle call function, out to the calc area, which is being done right here, calculating this, and we have the radius right here. So this sends that value out, and that actually gets calculated. A function takes input parameters in its call, whereas a script does not. So notice that this has a specific way that you can call it. This is where the input value would go, the radians right here, whereas down here we don't have that format line at all. So suppose you need to pass multiple arguments. So some functions require more than one input parameter in order to run. And there's no reason why we can't do 2 or even more parameters than that. The input parameters are going to be specified in the heading. So we're seeing how we specify a single one. What we're going to do is simply just put a comma between them, and we're going to put more parameters there. Each argument is going to take a value. The number of input arguments needs to be equal to the number of input parameters provided in the function call. That is, the number of numbers that you send up in order to run the function needs to match the number that's required by the function. The order of the arguments will match the order of the arguments that's shown, so that's really important that you give them in the correct order. So here's an example of a function that uses multiple arguments. This is the cone volume. So the cone volume program takes 2 parameters, and this shown example, the radius will take the value of 4 and the height will take the value of 7. Let's just pull this out and look in a little bit more detail. Notice that we have function here to declare that this is going to be a function. The thing that will get returned is the out argument, and that is equal to the cone volume of radius and height. So the out argument is going to be equal to pi over 3 times radius, and this squared times the height. This is the formula for a cone. The input parameters should be radius and height. Here is a function call right here. So what this says is that 4 is the first number, which will go into radius, and 7 is the second, so that one will go into height. So when we run this, the radius will be 4 and the height will be 7. Here is the answer being shown on the screen, and we could also figure out the type, which would report the entire function. We need to also talk about local variables. So there's a variety of different types of variables, and that is where they are valid or where they have values that are associated with them. Local variables are going to be variables that are associated only with the function, and they exist only inside the function while that function is executing. Once the function is done and has returned its answer, then those local variables go away. That's important to understand because sometimes students think they can continue to use those variables outside the function. The only way you can do that is if in fact the items are returned, and then when those items are returned, they need to be caught by something out in main. The scope refers to the region of validity of a local variable, and that is only in the body of a function when you have a local variable. That means if you have a local variable, it's not going to be reusable out in main unless, of course, that's the specific one that you have sent out and returned and caught in the variable out in main. Local variables are like scratch paper for a function. When the function call is over, they disappear. This makes a lot of sense because if you had a function and you wanted to reuse it, you wouldn't want it to save information from the previous time you called it up. You'd want it to start over and use the information that you had just given it. Functions with local variables are exemplified here. So for example, here's a function call that will compute the out cost. And what this is going to do is it's going to be the cost of a cylinder. Suppose that you're going to measure a cylinder and that there's a certain amount of a cost in order to make the cylinder out of some material. So I don't know, you have some metal that you want to create a cylinder out of and you want to compute what the cost is going to be. So the cylinder cost is going to do this task for you. So the format of the call is the cylinder cost, and the input is going to be the radius, height, and the cost of the material that's going to be used to construct it. This will return the total cost to make this object. The radius and the height are going to be in inches, and the cost is per square foot. So what we're going to do is calculate the surface area in square inches. So here's the formula for calculating the surface area. Notice that it is basically the formula for computing the surface area of a cylinder, which is going to be 2 pi r h. And then we're going to have 2 times the circle caps on the end, which are going to be 2 pi r, and there's 2 pi r squared. And this will get you to the circled areas. So then what we can do is we're going to convert the surface area in square feet and then round up so that we can compute the cost of it using an approximation. So here the surface area is going to be using the ceiling function, which is going to round up, and then we have the surface area divided by 144. And so then to calculate the cost, we're going to have the output cost is equal to surface area times the cost. So getting back to this idea about the scope of variables, scope is going to refer to the area of where the variable can be used. Local variables are also going to exist on the inside of the function. Local variables are erased when the function completes, and therefore they cannot be used after the function is done. This is useful because functions can be used multiple times, each time with the value specified in the input. Local variables can be used again only if their value is returned. So if you don't return that value, then it means you're not going to be able to use it. Local variables, in contrast to variables that are defined outside the function, and they can be used again later on because they're not ending when the scratch paper goes away. They exist as long as the program is running, in contrast to local variables, which exist only while that function is running. So MATLAB, in fact, has a number of built-in functions and commands. So some of the commands we have encountered in MATLAB already are just predefined functions. So some examples of those are format, type, save, and load. A command is a special form of a function not requiring any input parameters other than strings or character vectors, and that does not return any values. So commands are shortcuts for the longer and informal function calls. So here's an example of using type, which is one of the ones that is a command. So you see what we can do is we can do type script1, which is what we've normally been doing. However, we can demonstrate that it is in fact actually a function. So here we go, type, and then we use the parentheses and the single quotes with script 1. This is the more formal way to call it. And you see that this way up here is the command is basically a shortcut for this. This will work as long as the input and output is not too complicated. All right, so then that brings us back to our bird's eye view. So today we've talked about algorithms and we've talked about MATLAB scripts. We've talked about why one would need scripts in order to write programs. We've talked about input and output. We've taken a look at a variety of scripts, scripts with input and output, scripts to create plots. We learned how to make all kinds of very nice graphs when we actually graph some data, or where we could just use a predefined function and substitute in some data. We talked about file I/O, what the load and save commands do, so that allows you to read in information and also to write out some information. We talked about user-defined functions, how to create them, and we talked about local functions and scripts, so that you can have a local function. You can call a local function using a script. And finally, we talked about commands and functions. All right, great. Well, thank you so much for joining us today. Oh, here it is in the summary form, which probably would have been more useful to discuss. Just to look ahead at what you're going to be doing in the next couple of weeks, what we're going to do is complete the practice problems in chapter 3 for your lab. They're going to be due at 10 p.m. on Wednesdays. Hopefully you're listening to this or watching this sometime soon around Wednesday, or perhaps you're watching it a little bit ahead of time, as your choice. What you need to do is work those practice problems in the book. There are 10 of them for this week, and turn those in for your lab. What if you work on it for an hour and 20 minutes and you don't finish? Don't fret, because in fact you get full credit as long as you've simply made a reasonable effort to complete the lab. The other thing you need to do is work on your homework. For that, you're going to complete any 10 problems from the chapter 3 exercises. They're due next Wednesday morning by 9 a.m. All right, then with that, it's time for me to sign off. Thank you so much for joining me. I hope you have enjoyed learning about programming, and I hope that you have found this video to be informative and helpful for understanding these materials. All right, let's see, where is this? All right, well then, with that, I'm going to say thank you very much, and I will see you next time. Bye-bye.